Welcome to Zero Knowledge, a podcast where we explore the latest in blockchain technology and the decentralized web. The show is hosted by me, Anna.
And me, Fredrik. In this episode, Anna and I hope to teach you a little bit about Merkle trees, what they are and what they're used for.
Hey, Fredrik.
Hello. Today we're going to talk about Merkle trees.
Yes, we are. It's a challenge. We're going to make an attempt to describe Merkle trees without a whiteboard, without any graphics, without any videos.
Would you consider this to be blockchain 101 still, or have we graduated into blockchain 102 at this stage?
I think this is definitely a step up. I mean, even doing the prep work for this, I almost feel like if you really think about it, this is into computer science 101, 102, I imagine.
Yeah, I didn't take computer science in school. I took physics, so I don't actually know when you introduce data structures. But yeah, 101, 102, I would imagine, something like that.
And this is coming to you right around the holidays.
The Christmas Merkle tree episode.
We figured we would use this time to tell a story about a tree. It seemed kind of relevant. So to start off this episode, we want to dig a little bit into the history of Merkle trees and who is Mr. Merkle. A lot of you may know that Merkle trees were originally conceived of by a guy named Ralph Merkle. When you're looking up this original paper, what you end up with is you get two dates. You have 1979, 1989. So Ralph Merkle was a PhD student at Stanford in 1979. And as far as I can tell, submitted this paper in 1979, which outlined, was for the first time, what we now know as a Merkle tree. He didn't name it a Merkle tree for himself. I think that's what actually came after. Now, this paper wasn't actually published for a full 10 years until 1989. And there's a little bit of a backstory. I mean, this is on Wikipedia. There was some guy named Ron Rivest who didn't do what he was supposed to do, or he passed it to somebody else, and that person went to a startup, and then, it just sat there for a long time. Now, since then, Ralph Merkle has also gone on. He's created all sorts of other things. He's quite well known, I would say, in cryptography and also in general tech. He's worked at Singularity University, and he's involved in all these different associations in the Valley now. But that's a little bit of a story of where this came from. And one other thing to note is Ralph Merkle worked at somewhere called Xerox PARC when this actually came out. And I had never heard of Xerox PARC, but in doing a little bit of digging, it looks almost like this was a branch of Xerox that had a similar format to something like Bell Labs. Bell Labs has come up in previous episodes as this, and I think especially nowadays, we look back on these laboratories, which were very well funded, where research could be done that spanned a very long period of time. There was a bit less pressure. And this research is coming out of that era. Now, fast forward today, Merkle trees are being used in blockchain technology, and that's what we're going to talk about today. So maybe to start on that, Fredrik, do you want to try to describe verbally what a Merkle tree is?
Any pun intended with give it a try?
Oh, yes, that will come in handy later.
Yeah, so it's it's a hard topic to try to explain without graphics. Obviously, when you talk about trees, you want to be able to draw these trees. And it's also hard for me to really try to explain such a fundamental thing that I sort of think about a lot or have dealt with a lot in my life. And a lot of these things seem obvious, and even like a Merkle tree. Oh, it's just a tree that you put in hashes and you're done. As a concept, I think it's very simple, but when you actually try to dig into the details, it can get a little bit hairy. And especially something talked about in blockchain a lot is Merkle proofs and And that's sort of the reason that we use Merkle trees everywhere, to be able to have these kind of light proving structure of proof of inclusions. But let's start on the fundamental level of what a tree is. And we'll start with the same example that almost everyone does, a binary tree. And if you draw a tree with the root at the top, that means there's a node there. And I guess the terminology is, nodes and branches and leaves, I would say. So a node is like one, square or circle in your tree that contains some information. A branch is something that leads to another node. And a leaf is a node that is at the end, at the bottom of the tree.
It's almost like, would you say that like from the root, you have branches off the root? So you're starting with this one entity and then it branches off into two. And in the case of a binary Merkle tree, it branches off into two, and then those two branch off into four, and then four branch off into eight.
Indeed. And so that's where the binary tree concept comes from, is when you always branch off into two, or if you're allowed odd numbered leaves in your tree, then it will be able to branch off into one other node as well, but or one leaf.
What I noticed in looking online for Merkle tree explanations or videos, this is almost always the starting point. So you will see a very symmetrical tree in front of you, and that will be basically the basis of this example.
Yeah.
And this actually does exist in a blockchain system. It's the basis of the Bitcoin Merkle tree.
Yeah. And I think something important to note is if you come from a computer sciencey background or have looked at binary trees before, I think that the difference in a Merkle tree is that we only have data at the leaves. There's no data in the tree itself. So when you talk about a binary tree, you might talk about a sorted or an unsorted binary tree, and then you talk about when you insert data into this tree, you actually insert it in such a way that you balance your tree, and the root node will have your middle value, and your rightmost leaf will have the extreme upper value. And so then you have a sorted binary tree, and you can use this to easily do binary search across all of your data and things like this. And it has a bunch of properties that allow these kinds of things. In a Merkle tree, we don't have any of that. I mean, it's not what it's for. It's the data is only at the leaves, and the nodes above the leaves are all hashes. And we can get into what the point of these hashes are. But we've debated different ways of explaining this, of trying to find a way of figuring out what the point of this is. And what it comes down to for me is to be able to construct a Merkle proof. So a Merkle proof is a proof of inclusion of some data in this data set. So let's say we have 4 values, A, B, C, and D, and we have this data set. We want to prove that C is in this. How do we do this? Well, we can provide the person with the entire data set and let them search through the data set to find C themselves. But this has obvious downsides. We need to send them the whole data set. Maybe for privacy reasons or bandwidth reasons, we can't do that. Or it's super costly to search through the entire data set. So let's construct an imaginary tree where at the leaf nodes, we have A, B, C, and D. We combine A and B together to form a node above it that has the value AB. And then for CD, we combine those two together to form a node above it that has the value CD. And then we combine those two together to form the root node that has the value ABCD. And of course, now we can send this root node to someone and say that, here's the root node of this tree. You can check yourself that C is included. This is the exact same thing as saying we just send the entire data set and let them search through it. So obviously, this is basically the exact same thing as just sending the person the entire data set and letting them search through it. So we need to do better than this, but now we have this sort of structure, this tree in place that we can do something with. So what we can do is that instead of just concatenating the values up, we actually take hashes of the leaf nodes and produce those upwards. So the layer above the leaf nodes A, B, C, and D would be the hashes of A, B, C, and D. And so we have a sort of one link up that is, we have A, and then we have the hash of A. And then above those are the hashes of the hashes. So we concatenate those two hashes together and we hash that. And then at the layer above that, we hash, so second layer is hash of AB and hash of CD. And then at the top layer, we have the hash of those two hashes. So now at the root, we have a hash that is the fingerprint of the entire data set.
What if you are just given value C and you're asked to verify that that's actually in the data set? Right now, all you have is this root hash, which doesn't actually have the C value anywhere in it.
Right. So if everyone has the entire tree, then there's not much point in proving that some data is in that tree because they've constructed it and there's better ways of doing this. But the points that we're trying to achieve here is to be able to prove this data inclusion, to have this Merkle proof and prove to someone that only has the root hash. So if person A only has the root hash and person B wants to prove to them that C is indeed in the data set, what they would have to provide then is the hash of A and B and the hash of C and the hash of D and the value C. Because with all of this data called the Merkle path, the prover, the verifier, the person who actually only has the root hash, they can combine all of these hashes together and they can compare it to the root hash that they already have. And if they're equal, then yes, indeed, C must be in this data set.
That's interesting. So like the pieces of data that they're getting, it's not, you don't need a single line. You don't need C, hash of CD, and then root hash. You actually need C, hash of D, hash of AB, and the root.
Yeah.
And the hash of root.
That's
interesting. Right. So it's kind of like, because if you have AB, if you have the hash of AB,
you don't need any data underneath that because you can just assume this is not part of what we're trying to prove the inclusion of. So here's just that hash, and so you can, in a very large data set, when there's only 4 nodes, we're now still like providing 2/3 of the data of this tree. But in a very large tree, then you're really only providing quite a narrow path here, and it saves a lot of data in being able to prove this inclusion.
And what you're really looking for is you're basically going to run this system again, and if the root that you get at the end matches to the root that you are originally looking at, then you know that value C is correct.
Yeah.
One example that I found online, and I don't know if this will translate just on the podcast, but it was this example that Dan Finley from MetaMask used, which was about colors. So what he used in those leaf examples were different colors, and you're combining these colors as you kind of move up the tree. And so if you were to alter one of those leaf colors, that would inevitably at the end alter the root color. I'm definitely going to put that video in the show notes. It's a very short video. He just touches on Merkle trees for about 5 minutes, but I definitely liked thinking about it that way.
Yeah. And so I think for anyone who is familiar with hash functions and has worked with that, I think it's natural, like, because we are hashing all of the data at the leaf nodes and then hashing and rehashing all the way up, then of course changing any leaf, any data at all will change a bunch of the hashes along the way, all the way up. I think the color example is a pretty natural way to think about this. And if you don't have this sort of natural intuition of hash functions, then I think that's a really good way to think about it.
It's a good example, but like, now let's imagine we had thousands or millions of leaves and you changed one color slightly. It may be pretty much unrecognizable at the end. Whereas with hash functions, you will always, it will be a distinct change. It will be a traceable change, no matter how small that distinction is at the leaf level.
Yeah. So maybe we should look at an example here and just talk about use cases of Merkle trees a little bit and sort of it exists in Bitcoin and obviously in Ethereum, but we can talk about Bitcoin first because it has this very sort of simple binary tree structure and Merkle tree. So in Bitcoin, Merkle trees are used for transactions in a block. So every block has an associated Merkle tree that is constructed from all the transactions in that block. So your leaf nodes are transactions, and so you take the hashes of those transactions and propagate them upwards. And what this provides is a simple way to prove transaction inclusion in a block. So I can convince a light client, for instance, that only holds this Merkle tree root, that transaction X, which, let's say is I move money to you, is actually in that block. So I can prove to you, hey, I've sent you the money, it's in this block, and can send you that proof, and you can be convinced that that is actually what's happening in that block without downloading and executing the entire block yourself.
And so I think you already mentioned this, but like there's no data in these higher level hashes, but the actual data in the Bitcoin example is a transaction.
Yeah.
And like now my question is actually like, where does that, it's like a side question, but where does it live? What would that look like? What is the leaf in Bitcoin?
Yeah, it's a transaction data, like a binary blob of transaction data.
All right. And once it gets hashed, though, then it will be a distinct number of characters, and that will be uniform like all the way up. Even though you're combining them, you're combining these hashes, it's always going to do... How long is it actually in Bitcoin?
I don't know which hash function they use for this, actually.
Okay.
But I think this is an important note that I forgot to mention earlier, actually. We were talking about this example of just propagating concatenating the data upwards, and that sort of leads to larger and larger nodes, and like with larger data size in nodes higher up. And that's obviously not how we want this to work. And so if we have this hashing structure, then indeed all of the nodes above the leaf nodes will have the same size. They will all be the like exact same thing except different hashes in them. And this gives us some nice properties in terms of constraining or controlling the size of this tree.
We just covered the basics, the Bitcoin binary Merkle tree. In Ethereum, Merkle trees are often cited, but the way that they're built is quite different.
Yeah.
And even the way that they're spelt is quite different.
Yeah, indeed. And this is actually pretty funny because there seems to be no consensus in the world on how you pronounce this other thing. So the other thing is a prefix tree. So the example we talked about before was a binary tree. There are obviously all sorts of trees and tree structures, and with different properties, different efficiencies, etc. A prefix tree is a tree where you have both a key and a value. So in a normal, like in the binary tree we talked about before, there's no key. It doesn't exist to try to search for data in this tree. There are only values. And in the Bitcoin example, transactions are the values in this tree.
And also the hashes of those transactions. That's the only thing that's propagated up.
But in a prefix tree, we have a key as well. So the prefix part of it is referring to this key. So instead of having this binary structure where every node branches off into two other nodes, you have sort of an index of what I call it, an index of possible key values that you can move to from this node. So yeah, that's a prefix tree. We can dig into a little bit more about this key value structure later, but a prefix tree is usually called a trie, or I pronounce it tree still because it's TRIE, and that name comes from that it's a retrieval tree. It's optimized for retrieval of data, or sort of searching of data in this tree, and that's why you have this key value structure. And in retrieval, it's still pronounced tree, and therefore, like, it should be pronounced tree in my opinion. But for the sake of actually making this somewhat clear, I will pronounce it trie for this podcast.
So this is the Merkle, the non-binary prefix Merkle trie.
Right.
Spelled TRIE.
And in Ethereum, there aren't Merkle trees, there are Merkle tries. So in the Ethereum example, the key that we have is, it's actually, I think, the hash of the address, but for the sake of clarity, we can call it the address. It's functionally the same. The address, your Ethereum account address, is the key, and the value is your account state. So let's for the sake of simplicity, call it your account balance. So if you have 1 Ether, we want to find out how much Ether you have. We look in this trie for your address. And we look for this address what's called nibble at a time. And a nibble is 1 hexadecimal character of your address. And so at each node in an Ethereum trie, there are 16 of these indexes that I was talking about before. So in every node, it branches off into 16 other nodes, depending on what the hexadecimal nibble is that you're looking at. So you take the first nibble, and then you move down the tree based on what that was. Then you take the second nibble, move down another step. And with SHA-3 being 256 bits, that's 32 layers before you reach your account data. And this actually sort of brings us to another part, and we lied a little bit. Ethereum doesn't use Merkle tries, it uses Merkle Patricia tries, but that's just for optimization purposes. So we don't really need to think about it for the purpose of understanding what this is about. I don't think the Patricia part actually matters.
I sort of want to go over this again, because I know that, before we started recording this, we definitely went over it a couple times. And yeah, I had to sort of look at this trie from a few different angles before it made a lot of sense. What I took away was that at every node, at every level, there'll be 2 distinct pieces of information. One is a hash. It's basically a hash of the node underneath it. And the other is something that we've been sort of referring to as an index, which can also be described as the address. And
the index is more like reference to the other branches that comes after this one as it relates to that particular nibble. So the address is the key. It's the whole thing that we're trying to look for in this Radix tree, prefix tree that we're trying to search.
To go back to the earlier example, the Bitcoin example, the hashing and the sort of hashing upwards, this would actually be happening in a similar fashion from what I understand. It's not binary, so it's not always 2 by 2, but you are hashing upwards level to level. And the hash will always be the same size, no matter where you are on the node. So the difference is that you can use, like if you'd like to actually go from the root to the leaf, you can use the index and the nibble of the key to move from a root node to the nodes underneath that all the way down to the leaf.
Yeah. So if you wanted to build the simplest possible implementation of an Ethereum client, you would only have this trie, and you would use it to actually find the account balances and things. For efficiency reasons, it's better to have 2 separate data stores, one for the trie and one for the data, and use a key value database and implementation details, as we call it. Yeah, so I think that's an important distinction, where in the Bitcoin example, if we wanted to find a particular transaction, say we're looking for a transaction with some hash, we have no means of finding it other than a linear search through all of the transactions in that block. And if a block contains 100 transactions, that's actually not that bad, and that's a totally viable way to find a particular transaction you're looking for. When you're talking about the state trie in Ethereum, where there's millions of accounts and you're looking for one particular account, then doing a linear search through all of them to find one with this particular account number is not a reasonable way to find that account. So then finding it by this prefix tree is a relatively simple process. You follow 32 steps down and then you have it. You've found it. So you never really need to look in more than 32 places. Whereas if you did a binary search, it might be less, might be more, depends on what the structure of the data looks like, etc. And then you'd have a bunch of other overheads of trying to sort this data, etc. So it is actually a useful way to find the account data of a particular address. And so it does serve those two purposes. You can find it, but you can also, the exact same thing as in Bitcoin, if we have a light client that only has the Merkle root of like what we call the state roots, so the Merkle roots of the entire state database, then we can say, I have 5 Ether and I can prove it to you by providing you the path to my account.
So if you want to think about this path, the way you think about it normally is you'd go, okay, the root, and then you kind of follow a line down directly to one leaf. But when you're trying to prove these things, you don't actually get each hash on that path. Like if it branches out into 2, you will get the hash of the branch that your transaction is not on.
Exactly. So you need to, like, for someone that knows like tree pruning algorithms, it looks like a pruning algorithm where you take the hashes of all of the branches that indeed, like you said, my account is not on, because I can reconstruct the one that I'm on. I mean, that's the entire point. So the purpose of this proof is to provide all the information needed to reconstruct the roots. So to reconstruct the root hash, I need to provide the data itself, and then I can reconstruct all of the hashes above there. But I don't necessarily have the data of all my sibling nodes, so I need to provide the hashes of those, and they are then used to construct the hash above. And so indeed, you need to provide all the data necessary to be able to construct the root hash. And usually, again, this is a relatively narrow set of data of the entire database. So if at the top level, you prune away everything below a branch that isn't. So if you have 16 branches at the top, then you prune away 15 of them by providing the hashes at that level and then not anything below. So indeed, you basically prune 15 out of the 16 at every level.
And I think you can do that because if you think about the structure, whatever hash sits above other hashes takes them into account.
Exactly.
So you no longer need those individual hashes underneath it. You only need the top hash in that part of the trie that's relevant to you. We've sort of hinted at what we can include in the leaves of the Merkle trie in Ethereum. So like in the Bitcoin Merkle tree, you can include transactions, but you can also include balances.
So in Ethereum, we have 3 tries. One is the states trie. That is for the global states of all accounts and balances and contracts and stuff like that. The second is for transactions. So the same as Bitcoin, this is a per block trie that just is used to prove the inclusion of some transaction. And the third is the receipts trie. So a receipt is the result of a transaction, who sent what to whom, and kind of if it was successful or not, and some logs or output from that and things like that. So it is these 3 tries that exist in Ethereum.
And they they're distinct. They don't interact with one another.
No.
Do you are you getting, because where does the Merkle root live? I feel like we touched on this when we were explaining block headers and blocks and stuff. So if you have 3, are there 3 Merkle roots in every block?
Yes.
Oh, nice. Cool. I didn't know that. You don't Merklize all of them, huh? You don't want to make an uber Merkle root.
You could, but not much point in doing it for 3. Maybe if we had, hundreds of Merkle tries, then we would want to do that. But no, it's just those 3 stored in the header.
And they're actually stored in the header, not in the block.
Yeah.
Okay. How long are each of those?
So Ethereum uses Ketchak 256, so it's 256 bits. But yeah, it depends on which hash function you use. So I think an interesting part of Merkle trees and everything here is you can use it with any, like it's not tied to a particular hash function, obviously. Like you can hash it in whatever way you want. If you want something super secure, then you use a super secure hash function. If you are just trying to do some, kind of simple data proof thing, maybe internally, then you can use like these super fast hash functions that are less secure but can process like gigabytes per second. Kind of, it's an interesting like knob to tweak in a Merkle tree, and I think it sort of goes back to the history as well, and like what hash functions were available in '79 when Ralph Merkle wrote about this. I would be curious to see. I looked quickly at the paper, and the hash output was 100 bits, which is quite a lot. Like I'm not sure how practical it was for computers to produce those hashes, but I really don't know what kind of hash function it is, so I'd be curious to see.
In general, like I think that was something that also dawned on me as I was reading about it, and we were talking about this, that back then, a lot of this was very theoretical. This wasn't necessarily going to be used immediately in production. Now we can see it. It seems completely usable, not creating things that are too big or too intensive for the machines that we have at all. And it kind of reminded me a little bit of some of our previous episodes where we've interviewed people who are talking about more theoretical stuff that at this point is still has one foot in academia. And even though there's maybe some very fresh use cases in practice, real implementations, but they're still so very much demos or just sort of, to show that it's possible at all, but they're not yet ready to be used in large scale production. This makes me quite hopeful. I'm just thinking, wow, it's possible this, some of the stuff that we're talking about that seems almost impossible now will very soon be used. You can see kind of that like other things need to come into play before these things can actually be used in the real world sometimes. Like either the machines have to catch up or some additional research on specific parts need to come into the fray. Yeah.
I think it might be useful again to like summarize a little bit, and we can look at trees versus tries. What are their differences and why are we, bothering with both? So an obvious thing with a trie, as we talked about, is to be able to have this index to actually have a key and a value and be able to search through it. But obviously, well, maybe not so obviously, it depends on how much programming you've done. A prefix tree is smaller. I mean, depending on what your key space looks like, it will be smaller than a binary tree. So in a binary tree, like you said, you're always pairing up. So you're always just, two branches on every node, which produces a very large tree if you have a lot of leaf nodes. But in a prefix tree or a trie, you can actually, have 10 or 20 branches off of a single node. So you don't need to necessarily pair those up. So you'd have like a whole pyramid. You can just go down a more narrow line and exclude many more branches at every layer. So it's essentially a more efficient data structure, especially for the key space that we're looking at in Ethereum.
As I've understood, even though you can go in both directions, often even the Merkle tries in Ethereum are still being used in a similar way to those in Bitcoin, in that you're verifying that specific leaves are indeed correct by proving upwards to having two Merkle roots and comparing them and making sure that they're identical. And if they're identical, then we know that the information, the leaves, are correct. I think we talked a little bit about this, but like I still am a bit stumped on what use cases there are for going from the top down. Does it actually get used ever?
Like this goes into database design, and we use RocksDB. RocksDB has some algorithm to go from that key to the value, and I think it's more efficient than a Radix tree, but how much more efficient, I don't know. And this is, I think, using a Radix tree to find this data is actually a valuable, it is a real way to try to find data on disk. Like if you have a value stored on disk, you need a way to find it. Like there's no magic here. We can't just say, give me the data corresponding to this key. We need to somehow translate that key into something that we can store on disk that references another location on disk. And so how you do that is, up to you, but a Radix tree is one way to do it. So you store this whole Radix tree. You know that the disk address of the root is this. You can kind of get that from the operating system, from the whatever, or hard-coded in C or program. And then you can go one nibble at a time until you find the right place on disk to find this value. So I think it is a legitimate way to do this search. And I just think, database engineers have invented better ways to search for data since then. So we might not use that, but I think,
You just mentioned a term that I don't think have fully defined, and that's this Radix. Do you say Radix tree or Radix trie?
Well, I would normally say Radix tree, but for the purposes of this podcast, I will say Radix trie from now on. I think I said tree before.
Just apologies to anyone who's been a little mixed up. We're trying our best to use this lingo just for this podcast. Obviously, everything that we're sharing, we always think of the podcast as sort of an addition to study. So if you are studying this, sorry if we got it wrong a couple times. And we also think of it maybe as like, it's an introduction. So if you want to dig in, we're going to share a lot of, especially for this episode, we're going to share a lot of show notes, a lot of diagrams, papers, other videos for you to dive in. But now back to this question of a Radix trie. This Radix, as far as I understand, is also related to the Patricia trie. So what are these? These are words that we hear specifically in the context of Ethereum. How does this relate to what we've talked about?
Yeah, so Radix, actually, now that I think about it, I don't know if you do say Radix tree or Radix trie, because you would say prefix, like a prefix tree is a trie, and a Radix tree is a prefix tree with some optimization. So
yeah,
I'm not sure. But that's basically what a Radix, let's call it trie, is. So it's a prefix tree that has this index structure. But instead of naively taking one nibble at a time, let's say that there are two following nodes that don't branch off. So if in the Ethereum example, there are two addresses that share a common structure, and there are no other addresses that share any of this structure. So basically, we can take two nibbles and put them together into one node. So it's an optimization step that we can kind of squash this tree together a bit if there's shared index structure between different values, or shared key structure.
It's the shared key structure. It's not shared hash.
Shared key structure is the right way to think about it, because the other thing is sort of a fallout of having a shared key structure. Yeah, if it shares like several nibbles of the key, then you might as well just bunch them together in one node.
And I think for our purposes, we can just think of it like it's a way to optimize these tries. It's a way to make them, I guess, less heavy because you're sharing
smaller
nodes.
And faster to search through. And so, Patricia trie, which is, the Ethereum tries are called Merkle Patricia tries, or even modified Merkle Patricia tries. And Patricia stands for Practical Algorithm to Retrieve Information Coded in Alphanumeric. So, yeah.
I thought it was maybe Ralph Merkle's wife, but her name is Carol. So...
Yeah, so it's just an optimization on how to retrieve information and how to optimize search in this tree.
So that, in a way, kind of brings us to the end of our explanation part of this podcast, which will be the majority of it. We've covered this Merkle tree concept. We've covered the prefix tree or trie. We've described the different pieces of data that would be used in the Ethereum version of the prefix tree or Merkle trie, and how these exist in the blocks. We've gone kind of up and down through these to try to help to describe them. But now, why don't we cover a little bit of like, how does this work in the world?
Well, it's been created to be able to have like clients. And so that does indeed work. I mean, it serves its purpose for that. But these tries are very expensive to produce, actually. So I think that's the problem that we have with state bloat. It's not that the state takes up 8 gigs of drive. Who cares about 8 gigs? It's not that much. But the fact that this trie is so large, and if we execute a transaction, especially like a smart contract, it might touch 10 different accounts. So we need then to update not only the values on all of these places, but we also need to update all of the hashes going all the way up. So, if you touch just a few addresses, then that produces a ton of changes in this trie. And it can actually, if you introduce a new address that kind of splits off a previously shared key space, then you now might need to rearrange and reorganize this trie a bit. And so making all of these modifications to the trie is really hard, and they happen at like 200-300 modifications per second when processing a block. And this trie still needs to be saved to disk. So, all of these hashes, all of the structure, everything needs to be saved to disk. So the question is, how do you do that? And we use RocksDB for it, and it's not the best to do that. What we would ideally want is like a trie database that is specific for storing the structure. And so when you have 200 updates that you want to make to this trie, you don't go and touch the disk in 200 disparate places and cause a bunch of IOPS. You want to, be able to flush it in a linear fashion or whatever, one could dream up of. But this is a super hard problem, designing a database from scratch, specifically tailored to this use case. And, it's something that we at Parity have an open job position for, but, we'll see if we can actually get anything done there. But it's a big problem. And that's led to a lot of the experiments behind TurboGeth and trying to find like trie-less data structures to be able to do the same thing, to be able to provide the same proofs. And like in the future, maybe ZK snarks or starks or other proving structures come into place where we can provide the same like-line proofs without having to maintain this trie.
Yeah, I think that's definitely an interesting idea of like how these tries are not fixed things that, these are not static entities. Any change in one piece of it will inevitably need changes all through it. I guess I don't fully get what kind of weight or what kind of effort, space, computational power this really takes. But do you see it truly as like a strain on the system?
So it takes almost no computation power, but it's limited in your hard drive. So the reason you can't sync Ethereum on a normal hard drive anymore is because you need to update this trie so much. And a normal hard drive just can't skip around on disk and update these hashes all over the place that fast. And so we need an SSD to be able to have random access fast enough to do this. Ethereum in a very large way is IO bound. It's bound by the hard drive speed that you have. And if we didn't have this trie, then we could remove that IO bound, and being computationally bound would be a huge improvement.
Well, I think this has been a really intense, truly blockchain 102 experience.
I always have a hard time figuring out if this is useful or not. Like with the feedback we get, it's sort of like, yeah, it's cool, and some people really like it, but I have no idea if I did a good job at explaining any of this. So if you want to give feedback, check out our webpage, Twitter, email. We have things to provide feedback. I would love to hear it.
Yeah, definitely. We also have a Telegram group you can join and like immediately ping us. I want to say a little shout out to a project that sort of inspired this. At least it inspired the timing of the recording of this. And that's this event that Robbie Bent kicked off last year in Toronto called Merry Merkle, which is it's like a charity event. It's focused on, it's basically coming out of the Ethereum ecosystem. And they did it again this year in Africa, where they went and built a school. And I liked the name and I thought it was quite merry. So yeah, we decided we would just do an episode on Merry Merkle trees. So I hope that you guys enjoyed it. And like Fredrik said, please do share some feedback with us about this. If you want us to keep doing episodes like this, if there are other topics you'd like us to cover, we really, really like to hear from you.
And to our listeners, thanks for listening.
Thanks for listening.